This is our fourth lecture on flow in our Industrial Control Systems course. Pages 112 to page 119. We'll be looking at measuring flow rate using orifice plates and venturis. The head loss or pressure drop between 2 points along a pipe divided by the distance between those 2 points is the head loss per unit length. For example, pascals per meter. And we're giving this the symbol I. And I increases with fluid velocity according to the relationship shown here, K times V to the N. For laminar flow with Reynolds number below 2000, N is approximately 1, but when Reynolds number exceeds 4000, as in turbulent flow, N is approximately 2. Take a look at the relationship here. So again, for laminar flow, the head loss per unit length versus velocity is approximately linear because N is equal to 1, so I is simply K times V. For turbulent flow, head loss per unit length increases dramatically with velocity because N is 2 for turbulent flow. In experiment number 8 on the flow table, you did an experiment where you measured and plotted head loss versus length versus velocity, and indeed found this curvature to your graph. If we plotted head loss per unit length versus velocity squared, we then expect a linear relationship. Take a look at page 113, some more terminology. Have you ever noticed that when water rushes through a small opening like a tap, notice that it actually constricts after it leaves the orifice? Notice the cross-sectional area is narrowing down. The area where the cross-sectional area is the smallest is called the Vena Contracta. Vena reminds us of the word vein, or flowing, and contracta, of course, contract. What's going on here? Well, when liquid rushes through a small orifice, a small opening, it has to channel to the middle, and that motion continues beyond the exit of the orifice point. We have some calculations based on this. The coefficient of contraction is the cross-sectional area at the narrowest point at the Vena Contracta divided by the area of the orifice, cc, coefficient of contraction. And in the case of a sharp-edged orifice, it's about 0.65. We're saying that the area at the contraction is about 65% versus the area of the opening. The coefficient of velocity, CV, is the actual velocity that one would measure at the Vena Contracta divided by the theoretical velocity as calculated by Torricelli's theorem. And here's Torricelli's theorem. If you recall, V equals root 2gh. As always, the actual velocity is less than theoretical because of energy lost due to friction. If we multiplied each of these velocities by area, we would in fact get flow, because recall Q is equal to A times V. So the coefficient of discharge, or coefficient of flow, is the actual flow rate divided by the theoretical flow rate, simply obtained by multiplying each of these by their respective areas. We're going to use some of these terms upcoming. Page 114, we're going to look at how to calculate flow rate in pipes using venturis and orifice plates. A venturi is a streamlined constriction in a pipe. An orifice plate accomplishes the same thing. The fluid, the liquid, has to funnel through a small opening. There's a constriction. When the fluid enters the narrow section of pipe, it has to speed up because the flow rate is constant. And that increase in kinetic energy must occur at the expense of some other form of energy, which is pressure. And that's what these manometers are telling us. The pressure in the pipe is greater than the pressure in the throat of the Venturi. And the difference in height between the two indicates the difference in pressure. And from the difference in pressure, we can calculate the flow rate in the pipe. Now, in the first case that we're seeing, these manometers sit immediately above the pipe. And so whatever process fluid is running through the pipe is the same fluid that's in the manometer. Could be water, could be oil, some other liquid. The disadvantage of this type of manometer setup is that the manometer tubes might have to be very high, very long, tall. A more practical arrangement would substitute mercury as the manometer fluid. Mercury, being 13.6 times denser than water, would require much smaller manometer tubes to accomplish the same thing. So here we have process fluid flowing through the system, mercury, a different fluid in the manometer. Once again, the difference in height of the mercury column, or the difference in height of the manometer fluid, indicates the difference in pressure, from which we will calculate the flow rate or velocity of the fluid. A third possible arrangement is shown here, where the manometers sit below the pipe, and in fact the process fluid fills the manometer with the exception of the mercury, so there's no air in the system. In the first case, we can calculate from the difference in height, we can calculate the difference in pressure using the pressure depth equation. The difference in pressure would be density of the fluid times G times H. Pressure is rho GH, recall? In the second case, we use the same formula again. Delta P is rho GH. Just remember that in this case, the density is that of mercury, not the process fluid. In the case of manometers below the pipe, the formula is a bit different. Difference in pressure will be rho GH for the mercury manometer minus rho GH for the process fluid. Now, since H is the same, the height here is the same as the height here, we can factor out both G and H and come up with delta P is delta rho GH. On page 115, I'm going to try and prove to you that those formulas are correct. This arrangement is called a bifluid manometer. A bifluid manometer has two fluids in the manometers. Now, follow with me here on this derivation. We can say that the pressure is equal here and here along this red line. Why? Because those are horizontal levels in the same liquid. What is the pressure at this point on the left? Well, it's everything above it. So we could add those up. P2 would be the pressure here in the pipe, plus X centimeters of water, plus 13.6 centimeters of water would be the total pressure at this point that I'm coloring red. And that is equal to the pressure over here, horizontal levels in the same fluid on the right. What's the pressure over here? Well, P1 is the pressure in the throat of the Venturi, plus X centimeters of water again, plus 13.6 centimeters, but this time it's centimeters of mercury. Well, fortunately, we have the same X centimeters of water on both sides of the equation. We can cancel those. Therefore, I can write P2 plus 13.6 centimeters of water is equal to P1 plus 13.6 centimeters of mercury. Now I want to combine those heights of fluid. They will need to be in the same fluid. So let's convert 13.6 centimeters of water into centimeters of mercury. We do that by multiplying by the ratio of specific gravities. And as you know, 13.6 centimeters of water exerts the same pressure as a small amount of mercury because mercury is much more dense. So you want to make this number get smaller, multiply by a ratio that makes it get smaller, 1 over 13.6. And so we get then 13.6 centimeters of water is equivalent to 1 centimeter of mercury. Recall that P2 is the pressure in the pipe, and that's greater than P1. So if I take P2 minus P1, that's delta P, and I'll calculate that to be 13.6 minus 1, or 12.6 centimeters of mercury. So I'm saying to you the difference in pressure between these 2 points is actually 12.6 centimeters of mercury. Let's show that, in fact, this is a valid calculation for delta P. Take the equation we had on the previous page. Delta P is delta rho GH for the mercury minus delta rho GH for the water. H is constant, so we'll just call it H. And we'll factor out the densities, and we have delta P is the density of the mercury minus density of the water times GH. That's the formula I presented on the previous page, and this is valid for a bifluid manometer. All right, let's equate these two. We calculated up here that the difference in pressure is 12.6 centimeters of mercury. Let's convert that to dynes per square centimeter using atmospheric pressure as a conversion factor. 76 centimeters of mercury is equal to 1 atmosphere, which is 1.01 times 10 to the 6 dynes. So we get a value of pressure difference of 1.68 times 10 to the 5 dynes per square centimeter. Using this pressure depth equation, delta rho GH, we have 13.6 grams per cubic centimeter minus 1 grams per cubic centimeter, which is 12.6 grams per cubic centimeter times the gravitational constant times the height, is in fact the very same pressure. So the point to be made here is that the difference in pressure between these 2 points arises from the difference in pressure in the pipe and the Venturi. And that's 12.6 centimeters of mercury is the difference in pressure. And that can also be calculated using our formula, delta P equals delta rho GH. Take a look at page 116, please. We've just made the case that difference in pressure can be calculated using rho GH for a single fluid manometer, or difference in pressure would be delta rho GH for a bifluid manometer. We're going to use these two formulas in a derivation that will allow us to calculate the flow rate in Venturis and orifice plates. We'll start with Bernoulli's equation. Recall that the total mechanical energy of a fluid is constant, neglecting friction, and that mechanical energy consists of a pressure term, elevational potential energy, and kinetic energy. In the case of a Venturi or orifice plate, the elevation is constant, so we can just eliminate the elevation terms. Let's then calculate the difference in pressure. Recall that P2 is in the pipe, and that's greater than in the throat. So let's take P2 minus P1 is equal to 1/2 rho V1 squared minus V2 squared. Now recall from the continuity equation, Q equals A1 V1, we can rearrange to solve for V1. V1 is V2 times the ratio of the areas. We'll put that in here for V1. That'll eliminate one unknown. This rearranges to difference in pressure is P2 minus P1 equals 1/2 rho times V2 squared times the area ratio squared minus V2 squared. We can factor out V2 squared, and rearranging gives us this equation for V2. V2 is equal to the ratio of 2 delta P over rho over the ratio of areas. And since area can be written as pi d squared over 4, let's substitute those, cancel out pi and 4. We come up with an equation for velocity in a pipe using the ratio of diameters and the delta P and the difference in pressure measured across the manometer and the process fluid density. We ultimately want flow, so we simply take our velocity multiplied by the area, the cross-sectional area of the pipe. We'll have Q in the pipe is equal to A2 times the velocity in the pipe. Now let's consider the various cases. This delta P is rho GH. For a single fluid manometer, this density is the density of the manometer fluid. This is the density of the process fluid. If, in fact, the manometers are situated above the pipe, as we have in the first case here, then the density of the process fluid is the same as the manometer fluid, and these densities will cancel, and the equation becomes a little simpler. If we have the second situation where we have two different fluids, one fluid in the manometer and one in the process, we need to consider both of those densities. Just keep in mind which is which. This is the process fluid, this is the manometer fluid. When you have a bifluid manometer, when we have two liquids in the pipe, when the manometers are below the pipe, then we need to use delta rho GH, and that's the difference in the density of the manometer fluid versus the process fluid. This equation for flow rate works quite well, reasonably accurate for Venturis, where the streamlined nature of the constriction allows for little, if any, permanent pressure drop. So the pressure drop that occurs in the throat is pretty much recovered when it moves into the wider section of pipe. In the case of an orifice plate, because of the abrupt changes in direction, there is some permanent pressure drop, and so pressure is not fully recovered downstream of the orifice plate. As a result, that equation is not exactly correct. It'll need a correction factor. Take a look at page 117. This is the equation for the calculating the flow rate through an orifice plate, and it's essentially the same as for Venturi, except that we include a correction factor called the coefficient of discharge. Recall from way back on page 113, the coefficient of discharge is the actual flow rate divided by the theoretical flow rate. The theoretical flow rate calculated from Torricelli's theorem and the actual flow rate measured. And that ratio will be dimensionless depending upon the shape of the opening and the size, anywhere from 0.78 to 0.98. So simply a correction factor empirically determined to make our calculated flow rates closer to the truth. Take a look at this cross-section of an orifice plate. Notice multiple manometers show pressure increasing immediately before the plate and decreasing dramatically over the Vena Contracta, and recovering in part downstream of the orifice plate when the diameter again increases. But notice that the pressure doesn't completely recover. There is some permanent pressure loss due to friction that occurs during the dramatic directional flow changes through the orifice plate. Orifice plates are mounted by being bolted in flanges like here. Orifice plates often have the holes concentric. Occasionally they are eccentric, so picture that this is the internal diameter of the pipe here, and in this case the orifice is sitting right at the bottom of the pipe, and the purpose of that would be if solids were present they would tend to not collect in an eccentric orifice plate. Some are even segmental in shape. Let's take a look at problem number 9. Calculate the flow rate of water flowing through a 12-inch diameter pipe, given that when passing through a 6-inch diameter orifice plate, a pressure differential of 3.5 feet is measured, with a manometer containing a fluid with a specific gravity 1.25. So water is in the pipe, a different fluid is in the manometer. Assume the manometer is below the pipe, assume a coefficient of discharge of 0.970. I've drawn it here. Process fluid is water, specific gravity 1.0. Manometer fluid, specific gravity 1.25. Difference in height of the manometer, 3.5 feet of height. Coefficient of discharge 0.97. Diameter in the pipe here is 12 inches. Diameter in the Vena Contracta, or at the orifice plate, 6 inches. Here's our equation. Q, flow rate, is equal to the coefficient of discharge, which is 0.97, times the area of the pipe. Notice 2 represents in the pipe. 1 is in the throat. The area is pi d squared over 4. The diameter is 12 inches. I'm converting that to feet. Pi over 4 times 1 is 0.785 square feet. In the root, in the radical, we have 2 times the difference in densities. And this is because the manometer is below the pipe, and so it's a bifluid manometer. We have to use delta rho GH over the density of the process fluid. So the density of the manometer fluid is first. It's 1.25 times the density of water. I could have multiplied this out, but I think you'll find it's easier to solve if you keep them separate like that. Just say it's 1.25 times as dense as the process fluid, or water, minus the mass density of the process fluid, which is water, times G is the gravitational constant, 32.17 feet per second squared, times H, the height difference in the manometer, 3.5 feet, divided by the density of the process fluid, 1.9403 slugs per cubic foot, divided by the ratio of diameters to the 4th power. Well, the diameters are 12 inches over 6 inches. That's 2 to the 4th power, which is 16 minus 1, which will be 15. In the numerator, we can factor out the mass density of water, and then that divides by 1.9403 in the denominator of the numerator, which makes life a little bit easier. So we have 0.761 square feet times the root of the numerator, 2 times 32 times 3.5. Here we have 56.3, divided by 2 to the 4th power, 16 minus 1 is 15, feet squared over second squared. That gives us 3.75 feet squared over second squared, the root of which is 1.94 feet per second, multiplied by the coefficient of discharge, 0.761, gives us a flow rate of 1.47 cubic feet per second. Rather tedious, but not particularly difficult. Please take a look at page 119. We'll have a couple of problems related to Venturis. So problem 10 says calculate the flow rate through a Venturi meter having a pipe diameter of 10 centimeters, a throat diameter of 5 centimeters. The difference in height of water in the manometer is 6 centimeters, and the difference in pressure is measured by pressure taps above the pipe. This is the simplest possible case, and I have it drawn here. Water is the fluid in the pipe. The pipe diameter is 10 centimeters. The throat diameter is 5 centimeters. The difference in height is 6 centimeters. That's all we need. We're going to use the equation Q is equal to the area of the pipe times the root of 2 rho, rho being the density of the manometer fluid, gravitational constant, times height difference across the manometer, divided by rho. This rho is the density of the process fluid, but in this case they are in fact the same. The process fluid is the same as the manometer to it, so those are going to cancel as I've shown. Divided by the ratio of diameters to the 4th power minus 1. We need the area. So the area is the area of the pipe, that's pi d2 squared over 4. The diameter of the pipe was 10 centimeters. 10 squared times pi over 4 is 78.5 square centimeters. Cross-sectional area of the pipe. Times, again, notice the densities are gone, so it's simply 2 times the gravitational constant, 980.7 centimeters per second squared in the CGS system, and 6 centimeters was the difference in height, divided by the ratio of the diameters to the 4th power. Again, this is 2 to the 4th power. 16 minus 1 will give us 15. This numerator term works out to be 11,768, has units of centimeters squared per second squared. And taking the quotient, I'm going to then take the square root of 784.6 centimeters squared per second squared, which is 28 centimeters per second multiplied by the area of the pipe, 78.5 square centimeters, gives us a flow rate of 2,200 cubic centimeters per second, or 2.2 liters per second. There's one last problem to try. Problem number 11. Using the same pipe and Venturi dimensions as in problem 10 above, calculate the flow rate of water when the difference in height of a mercury manometer is 0.476 centimeters. Water is the fluid being measured. The manometers are below the pipe. So I've drawn that over here. So water is the process fluid. We have mercury manometers below the pipe. The dimensions are the same as in the previous problem. The pipe has a 10 centimeter diameter. The orifice, the Venturi, has a diameter of 5 centimeters. The height difference is 0.476 centimeters of mercury. We use the very same equation without the coefficient of discharge in it. We need the cross-sectional area. It's the same as in the previous problem. Pi times d squared over 4 came out to 78.5 square centimeters, times the root of 2. Now here's where the difference is. We have to use delta rho GH because our manometer is situated below the pipe and it's a bifluid manometer. This is the difference in the density of the two fluids, times the gravitational constant times the height difference across the manometer, and this rho is again the process fluid. The diameter ratios are 10 centimeters over 5 centimeters. That's 2 to the 4th power, which will be 16 minus 1 will be 15 again. So here we have it. 2 times delta rho. Now this is the density of the mercury here. 13.6 is a specific gravity times that of water minus the density of the process fluid, which is water, and divided by the density of the process fluid, which is water. So I can factor out 1 gram per cubic centimeter from the numerator and then cancel it with what's in the denominator, and I'm basically left with 13.6 minus 1, or 12.6 for this whole term right here. Well, actually here, all of this. No units. So it's 2 times 12.6 times 980.7 times the height 0.476 divided by 15, and that equates to 11,767 divided by 15 centimeters squared per second squared, the root of which is 28 centimeters per second, times the area of the pipe, 78.5 square centimeters, is 2,200 cubic centimeters per second. It's exactly the same flow rate as we had in problem number 10. I simply put the manometer in a different location to show you how the same flow rate will be indicated differently by a different manometer fluid and a different manometer arrangement. Just to conclude this lesson, let's briefly look at a comparison of these head meters. Head meters measure pressure, and so they're called head meters. We looked at orifice plates. Orifice plates are inexpensive. They're easy to install. They're maintenance free. Usually accurate to within 3 to 5%, which is pretty good. However, they may wear with time, especially if there's solids present. That would cause drift, and variable and unknown coefficient of discharge, which you need for the calculation, would require site calibration, and they do induce some permanent pressure drop. By comparison, Venturis should be a little more accurate and stable over time, less wear. They also introduce only a small pressure drop, minimal, but they are considerably more expensive than orifice plates. This brings us to the end of page 119. The last pages of theory on fluid flow, pages 120 to 128, describe half a dozen different types of flow meters that are used for pipes as well as sewers and drains. Rather than describing these in a video, I have posted a one-page document entitled CHM 614 Flow Meter Summary. It immediately follows this video on Blackboard. In that one-page document are a number of hyperlinks to short, very short, YouTube videos and animations describing and explaining and showing how these various types of flow meters work and their applications. And this will give clarity to the course notes. You should watch these as you are responsible for this material as described in the flow test summary, which is also posted on Blackboard. I've created one final video explaining how to solve the 21 fluid flow problems at the end of this chapter. Now I'm only explaining how to solve them in the video. Detailed printed solutions for all of these problems are posted on Blackboard immediately following the flow videos. And don't forget about the self-study unit on pipes, fittings, and valves, which will also be part of the final test. The content of this course is some of the most practical knowledge that you can bring to the workplace. And these are the words of Chem Lab Tech graduates. Thanks for watching.